So we're in the realm of inductive definitions, recursive functions, and efficient evaluation of these using memoization and dynamic programming. So we are looking at examples of problems where the main target is to identify the inductive structure. And once you identify the inductive structure, then the recursive structure of the program becomes apparent, from which you can extract the dependencies and figure out what kind of memo table you have and how you can fill it iterative using dynamic programming. So this is something which comes with practice, and by looking at more examples, hopefully the procedure will become clearer. But the key thing to dynamic programming is to be able to understand the inductive structure. So you need to be able to take a problem, identify how the main problem depends on its subparts, and using this come up with a nice inductive definition which you can translate into a recursive program. Once you have the recursive program, then the memo table and the dynamic programming almost comes out automatically from that. So this is a problem involving words. So what we want to do is take a pair of words and find the longest common subword. So for instance, here we have secret and secretary, and secret is already also inside secretary, and clearly since secret is the longest word in secret itself, the longest subword that is common is the word secret, and it has length 6. If we move to the next thing, bisect and trisect, then actually this should be isect. This is a mistake, which has length 5. Okay. Similarly, if we have bisect and secret, okay, then SEC. So when we say subword, of course, we don't mean a word in the sense, we just mean a sequence of letters. So SEC is the longest common subword. This has length 3. And if we have two very different words like director and secretary, then sometimes we might have only small things. For example, here RE and EC are examples of subwords, but there aren't really very long words which are common to these. So the subword is only length 2. So here is a more formal description. Right? So supposing I have two words U and V, so U is of length M and V is of length N, and the positions using Python notation are numbered 0 to M minus 1 and 0 to N minus 1. Then what I want to do is to be able to start at AI and go K steps. So I to I plus K minus 1 and BJ to J plus K minus 1, such that these two segments are identical. Right? So this is a common subword, and we want to find the longest such common subword. What is the K? Okay, we don't even want the subword. We'll find that the subword will be a byproduct. We first need to just find K. What is the length of the longest common subword of U and V? So there is a brute force algorithm that you could use, which is to just start at I and J in each word. You can start with position I in U and J in V and see how far you can go before you find they are not common. Right? So you match AI and BJ. Right? So if AI and BJ work, then it's fine. So this should be BJ. Okay. And if AI and BJ work, then you go to AI plus 1, BJ plus 1, and so on. And whenever they find two letters which differ, then the common subword starting at IJ has ended. And you say, okay, from IJ, I have a common subword of something. Now, among all the IJs, you look for the longest one, and that becomes your answer. Now, this, unfortunately, is effectively an order n cubed algorithm if we think of m and n as being equal, technically mn squared, because there are m times n different choices of I and j. And in general, I start at ij and then I have to go from I till the end, right? And from j till the end. So we have to do a scan for each ij. This scan in general adds up to an order n factor. And so we have order mn squared or order n cubed if you would like to do it. So our goal is to find some inductive structure which makes this thing computationally more efficient. So what is the inductive structure? Well, we have already kind of seen it. When can we say that there is a common subword starting at ij of length k? Well, the first thing is that we need this ai to be the same as bj. So I need this condition. And now if this is a common subword of length k at ij, then what remains of the subword, okay, namely this segment from I plus 1 to this and j plus 1 to this, must also match, and they must in turn be a k minus 1 length subword from here to there. So we want to say that there is a k length subword starting at ij if ai is equal to bj, and from I plus 1 and j plus 1 there is a k minus 1 length subword. So in other words, I can now write the following definition. I can say that the length of the longest common subword, LCW starting from ij. Well, if they two are not the same, if AI is not the same, there is no common subword at all, because if I start from here, I immediately have two different letters. So then the length is 0. Otherwise, I can inductively find out what is the longest common subword to my right. Start from I plus 1, start from j plus 1, find out what I can do from there. And to that word, I can add one letter, because this current letter AI is equal to bj, so I get 1 plus that. Okay? And the base case or the boundary condition is when one of the two words is empty. Right? If I have no letters left, if I have gone ij, I'm looking at different combinations I and j. So if either I or j has reached the end of the word, then there is no possibility of a common subword at that point. So when we have reached the end of one of the words, the answer must be 0. Right? So this gives us the following definition. So remember that u is actually of length m, so it has 0 to m minus 1. So what we will do is we will add a position of m to indicate that we have crossed the last letter. Similarly, v has 0 to n minus 1 as valid positions. So we will use the indices 0 to n. So if I becomes m or j becomes n, it means that that corresponding index has gone beyond the end of the word, right? So, so this should be m and this should be n. So we have that if we reach m, then LCW of m comma j is 0, because we have gone past the length of u. Similarly, if we reach n, then LCW of I comma n is 0, because we have gone past the length of v. And if we have not gone past the length, if we are somewhere inside the word in a valid position, okay, then the length is going to be 0 if the two positions are not the same, if AI is not equal to bj. Otherwise, inductively, I compute the length from I plus 1 and j plus 1, and I add 1 to it. Okay, this is the case when AI is equal to bj, because that segment I can extend by. So this is just stating in an equation form the inductive definition that we proposed in the earlier thing. So here is, for example, this bisect and secret. Okay? So we have position 0 to 5, and then we have the 6th position indicating the end of the word. And now remember that the way our inductive definition was phrased, ij depends only on I plus 1, j plus 1. So actually the dependencies are this way. So the arrows are indicating that in order to solve this, I need to solve this first, right? The value at 2, 3 depends on the value at 3, 4. Right? So in order to solve this, I don't need to solve anything, because everything is right. So in order to solve this, I don't need to. So anyway, okay, so we can basically, we have this simple thing which says that the corner and the right column and the bottom thing don't require anything, and we know that because those are all zeros, right? So we can actually fill in those values as zeros, because that's given to us by definition. And now we can start, for instance, we can start with this value because its value is known. So we will look at whether this t matches that t. It is that, so we take 1 plus the value to its bottom right, so we'll get 1, and then we can walk up and do the same thing. At every point we'll say that, okay, if C is not the same as T, so none of these letters, so if you look at these letters here, right, none of these letters are T. So for all of these letters, I'll get 0 directly, because it says that AI is not equal to Bj. Okay, so I don't even have to look at I plus 1, j plus 1. It directly says it's 0 because it's not there. So in this way, I can fill up this column. So this is like our grid path thing. I can fill up column by column, even though there the dependency was to the left and bottom, and here the dependency is diagonally bottom right. Okay, I can fill up column by column, and I can keep going. And if I keep going, I find an entry 3. Okay, so the entry 3 is the largest entry that I see, and that is the actual answer, this entry 3. Okay. And now we said earlier that we are focusing on the length of the longest common subword, not the word itself. And the reason we can afford to do that is because we can actually read off the answer once we've got the lengths. So we ask ourselves, why did we get a 3 here? Okay, so we got a 3 here because we came as 1 plus 2. So since we came as 1 plus 2, it must mean that these two letters are the same. Right? Similarly, we got a 2 here because it is 1 plus 1. So these two letters must also be the same. Okay, so these two letters are the same, these two letters. So finally, we got 1 here because this is 1 plus 0. So these two letters are the same. So therefore, these 3 letters must be the same. So if we walk down from that magical value, the largest value, and we follow the sequence, then we can read off on the corresponding row or column, because they are the same, the actual subword, which is the longest common subword for these two words. So here is a very simple implementation in Python. Okay, so all it says is that you start with the the two words, okay, U and V. You initialize this LCW thing at the boundary at the nth row and the nth column. Okay, and then now you remember the maximum value. So you keep track by initializing the maximum value to 0, and then you fill up in this particular case in column order. Okay, so for each column, then for each row in that column, you fill up the thing using the equation. If it is equal, I do 1 plus, otherwise I say it's 0. And if I see a new value, this is the thing where I update. If I see a new entry which is bigger than the entry which is currently the maximum, I update the maximum. So this just allows me to quickly find out what is the maximum length overall. And finally, when I've gone through this loop, I would have filled up the entire table, and I will return the maximum value I saw overall. So when we did it by brute force, we had an order mn squared algorithm. Here we are filling up a table which is of size order m by n, and each entry only requires us to check the ith position in the word, the jth position in the word, and depending on that, if necessary, look up one entry, I plus 1, j plus 1. So it's a constant time update. So we need to fill up a table of size order mn. Each update takes constant time. So this algorithm brings us from mn squared in the brute force case to mn using dynamic programming. So a much more useful problem in practice than the longest common subword is what is called the longest common subsequence. So the difference between a subword and a subsequence is that we are allowed to drop some letters in between. Okay. So for instance, if we go back to the earlier examples, for secret and secretary, there's no problem because the subword is actually the entire thing. And again, for bisect and trisect also, it's the same thing. But if we have bisect and secret, earlier if we did not allow ourselves to skip, okay, we could only match sec with sec. But now we can take this extra t and we can skip these two and match this t and say that SECT is a subsequence in the right word which matches the corresponding subsequence, which is also a subword in the left word. But in the right, it's not a subword. It's a subsequence. I have to drop some letters to get SECT. Similarly, if I have secretary and director, then I can find things like ECTR in both of them by skipping over judiciously. So why is this a better problem? Well, we'll see that. But effectively, what does skipping mean? Skipping means that I get segments which are connected by gaps. Right? So I get this segment. Then I want to continue the segment. So I look for the next match. Right? So I skip, but the next match must come to my right. So it must come to the right and below the current match, because I cannot go backwards in a word and start a match again. So I cannot, for instance, go here and say that this is an extension, because this requires me to go back and reuse the E that I have seen in sec to match the second D in secret, which is not allowed. Right? So I can keep going forwards, which in the table corresponds to going to the right and back, right and down. So I'm going increasing the order of index in both words, and I can group together these things, and this is what the longest kind of subsequence is. So we could in principle look at the longest common subword answer and look for these clever connections, but it turns out there is a much more direct way to do it in an inductive way. So the motivations, well, one of the big motivations for subsequence matching comes from things like genetics. For instance, when we compare the gene sequences of two organisms, they are rarely equal. So what we are looking for is large matches where there might be some junk genes in between, which we want to discard. So we want to say that two gene sequences or two organisms are similar if there are large overlaps over the entire genome, not just looking for individual segments which are long, but by just throwing away the minimal things on both sides, you can make them align, as they call it. Another important example is something called diff, which is a Unix command to compare two text files. So this treats, in fact, line by line two files as a word. So each line is compared to each line in the other file. If the lines match, they're considered to be equal. And this is a good way of comparing one version of a file with another version of a file. So supposing you are collaborating on a document or a program with somebody else and you send it by email and they send it back saying I've made some changes, then diff tells you quickly what are the differences between the file you sent and the file you got back. And diff essentially is doing the same thing. It's trying to find the longest match between the file that you sent and the file you got back, and the shortest way in which you can transform one to the other by changing a few lines. Right? So these are some typical examples of this longest common subsequence problem, and therefore it's usually much more useful in practice than the longest common subword problem. So what is the inductive structure of the longest common subsequence problem? So as before, we have the words laid out. Okay, so we can say A0 to AM or AM minus 1. It doesn't matter how you choose it, but in the picture it says AM, but if you want, you can ignore these last two entries here. Okay, so A0 to AM minus 1 is the first word, B0 to BN minus 1 is the second word. Right? And now there are two cases, right? The first case is the easy case. Supposing I have these two things are equal. Then, like before, I can inductively solve the problem for A1 and B1 onwards and add this. Okay? I can extend that solution by saying A0 matches B0 and then whatever matches. So what is a subsequence? A subsequence actually is some kind of a matching. It says that, it will say that, okay, this matches this, and then this matches this, these are the same, and this matches this, and then this matches this, and so on. Only thing is that these lines can't overlap. They must keep going from left to right without overlap. So this kind of pairing up of equal letters, the maximum way in which I can do this is a longest common subsequence. So now what we are saying is that if I can actually match the first two things, then I should match them. Okay, and then I can go ahead and match the rest as I want. Okay, and the reason is very simple. Supposing the best solution did not match these. Supposing you claim that the best solution actually requires me to match A0 and B1. Well, if I could match A0 and B1, I can also undo it and match A0, B0 and then continue. Because A0 and B1, if they match, then A1 must be matched to is right. Right? So I can take that solution and change it to a solution where A0 matches B0. So if the first two letters are the same, I might as well go with that and say it is 1 plus the result of optimally solving the rest. What if they are not the same? This is the interesting case, right? So supposing these are not the same, then what happens? So then can we just go ahead and ignore A0 and B0? No, right? So it could be that A0 actually matches B1, or it could be that B0 matches A1. We don't know. But we certainly know that A0 doesn't match B0. So we have to drop one of them because we can't make a solution with A0 matching B0, but we don't know which one. So what we do is we take two subproblems. We say, okay, let us assume B0 is not part of the solution. Then the best solution must come out of A0 to AM minus 1 and B1 to BN. B0 is excluded because I can't match it with A0, and whatever A0 matches must match to the right, so I must throw it away. But maybe this is the wrong choice. So the other choice would be to keep B0 and drop A0, in which case I do A1 to AM minus 1 and B0 to BN. Right? So these are two different choices. Which one do I choose? Well, since we don't know, we solve them both. Right? We solve, if A0 is not B0, we solve both these problems, A1 to AM minus 1 B0 and A0 to AM minus 1 B1. Solve both of them, take the maximum one. Whichever one is better is the one we keep. So this in general will take us deeper in the word. So we said A0, B0 will require to solve it for A1 and B0 or A0 and B1. So in general we have AI and BJ, right? So again, since we have AI and BJ, then we will use the same logic. If AI is equal to BJ, then it is 1 plus the rest. Okay, this is the good case. If AI is not equal to BJ, right, then what we do is we look at the same thing. We drop BJ and solve it. And symmetrically, we drop AI and solve it and take the better of the two. Right? We take max of the solution from I and the solution from J plus 1. So if we say, like we had before, that LCS of Ij is the length of the longest common subword starting from I and J. If AI is equal to Bj, it will be 1 plus the length starting from I plus 1, J plus 1. If it is not equal, it will be the maximum of the two subproblems where either increment I or increment J. Okay? And as with the longest common subword, Okay, when we go to the last position, okay, m and n, we get 0. So here the dependency is slightly more complicated because depending on the case, I either have to look at I plus 1 j plus 1, or I have to look at I plus 1 j or I j plus 1. Right? So I have, for this square, I have to look at its right neighbor, the right diagonal neighbor, and the bottom neighbor. But once again, the ones which have no dependency are clear. So earlier we had, for longest common sub word, we had only this dependency. This meant that even a square like this had no dependencies because there is nothing to its bottom right. But now, for instance, if we look at this picture, since we are looking bottom, right, and left, okay, if I look at this, its dependencies are in 3 directions. 2 of those directions are empty, but this direction there is a dependency. So I can't fill up this square directly. The only square I can fill up directly is this one because it has nothing to its right, nothing diagonally, and nothing below. Okay, so I start from there. So I start from there and I put a 0, and as before, we can go down this because now once we have this, we have everything to its left. Right? And once we have this, and because we are beyond the word, we are at this dummy position, the row and column become 0. But the important thing to remember is the row and column become 0 not because they have no dependency, but because we can systematically fill it up exactly like in the grid paths. We can fill up the bottom row and the leftmost column there, here the rightmost column. Now, once we have this, we can fill up this point. Right? And then again, we can, once we have three entries, we can fill up this. We have 3 entries, we can fill up this. We have 3 entries, we can fill up this. So we can fill up this column, and we can do this column by column. And we propagate it, and then finally the value that propagates here is our longest length of the longest common subsequence. We could also do this row by row. Okay. Now, how do we trace out the actual solution? Well, the solution grows whenever we increment the number. So we can ask, why is this 4? Okay, so we say that this is 4 because, not because we did 1 plus 3 because s is not equal to b, which is 4 because we got the max value from here. Why is this 4? Again, I is not equal to s, so we got the max value from here. Why is this 4? Oh, s is equal to s, we must have got it by 3 plus 1. Why is this? Because e plus e, so we must have got it from here. So we follow the path according to the choices that we made in applying the inductive function in order to generate the value at each point. So in other words, for each cell ij that we write, we remember whether we wrote it because it was 1 plus the diagonal neighbor or the maximum of the left and the right, in which case we record whether the left or the bottom was the maximum we picked. Now in this picture, every time we take a diagonal step, it means we actually had a match. So this is a match. Okay, the first one here is a match, s equal to s. This is a match, e equal to e. This is a match, c equal to c. Now, after this point, we are flat, and then at this point again we have a match. So we get s, e, c, and t. Right? So we can read off the diagonal steps along this kind of explanation of the longest number, largest number we got, and each diagonal step will contribute to the final solution. Now there could be more than one, so because we haven't got an example in this case, but sometimes the max could be one of, in both directions. If I'm taking the max of the left, the right neighbor and the bottom, they could be the same, right? So I could have a situation like this. Supposing I landed up here, then I don't know whether I got it from here or from here. So I might have 2 different extensions which lead me to a solution. So the longest common subsequence need not be unique, but you can recover at least one by following this path. So here is the Python code. It's not very different from the earlier one. So we can just see, you just initialize the last row and the bottom row and the last column, and then as before, you walk up row by row, column by column, and fill in using the equation. And in this case, we don't have to keep track of the maximum value and keep updating, because the maximum value automatically propagates to the 0, 0 value. So just like the longest common subword, here once again, we are filling in a table of size m times n. Each entry only requires us to look at most 3 other entries, the one to the right, the one to the bottom right in the diagonal, and the one below. So it's a constant amount of work. So mn entries, constant amount of work per entry. So this takes time m times n.